on deep learning. So any confusion from the topics of classicals? Okay. Yeah, try to brainstorm for the project ideas a little bit before the deadline. Okay, so you can have some solid ideas, because there are lots of nitty-gritty details, and your interest and your expertise and all those things should be taken into account before you choose a particular project to work on. So yeah, give time to that. All right, so we introduced the concept of a model, which is kind of a transformation which converts the given input to the expected output. So we saw that the input can be anything from an image, a text, an audio, all of those things, and the output label can be the type of the image, the translated text, or the captioning of the audio. And we saw a very simplistic example of a model which takes the vector x as input and multiplies this vector x with a weight vector w and adds it to a bias vector v to get the final output. So the task of the model is to find the suitable values of the parameters w and v. These are the model parameters. These are the transformation tools which convert x to y. So the task of the model training is to find the exact values of the parameters w and v which can convert x to output y. And we saw that we find the suitable values of the parameters by using the samples from the training dataset. We are given some candidate values of x and the corresponding values of y. So using those candidate values, all of which are encompassed within our dataset, we attempt to find the expected values of the parameters which map x to y. So the training function which does the task of finding the suitable values of the parameter is called the loss function. And it is called loss because we minimize the value of this function. So at first we assume that we have some random values for the parameters which is far from our desired values, the values which are expected for this particular model to work. It's far from those values initially. So the loss is large. We have a huge loss. So as the training progresses, the loss kind of diminishes because we are learning the values of the parameters better with each training epoch. We will see more details of that later. So typically that's the process of training. That using your training data, you try to find the mapping which maps x to y with the help of a loss function, which is a tool to find those exact values. And then once you have diminished the loss to a certain extent, you say that okay, now the model is well trained, and then you deploy it in real settings where you give the real life examples of input to find the expected output.
Yeah, are you at home?
So we saw that
Wait,
this
before you go
process
out,
is
can
rather
you
good,
bring on the
supposed to be
halal
good
chicken?
because
One
you
packet
are
halal
using your
chicken,
data
keep it
to
in the
find the
bucket
values of the parameters.
so that I can cook.
But we
and
saw
cook.
an issue with this approach which is called overfitting. That means the model can train itself
It's written
too
15
good
or
on the
17.
training data set. So good that it kind of just memorizes the data. So what's the problem with that? It doesn't capture the intricate relationship between the data that it should have captured.
Is not until you fall back.
Sorry.
Okay. Rather, it kind of blindly memorizes the data. So when we are in the inference setting, when we deploy it in real life, when the input values slightly vary from the training examples, we don't get the desired output. Because the model technically just memorized the data. It didn't learn any intuitive relationship that it was supposed to learn. So when we are training a model, we don't want the model to memorize our data. We want the model to capture the intuitive relationship which maps the x values to the corresponding y values. For example, this blue box is our model. So this model is characterized by the set of parameters theta, which we saw previously that it's the composition of the values w and b. So when given the image of this digit 4, this is our input x. The model produces the prediction vector like this, and we expect that within the prediction vector, the probability of class 4 should be the highest. The class 4 should be predicted. So that's the setting we expect out of the model. So in order to obtain that, we design a loss function like this, which takes the output function that it obtains from this input and also the expected output y, the level 4, and then tries to fit fx to y. So the goal of the training is that fx should resemble y. So here we see that the model output is a vector. This is a classification problem. So what's the output in a classification problem? It's a vector. And the number of values in the vector is equal to the number of classes. And each value in the vector represents some probability of belonging to one particular class. So when our input belongs to the class 4, what is the ideal value of the prediction vector? So it has 10 values because we have 10 digits, 10 classes, okay? And each value is the probability of belonging to each particular class. So what should be the ideal output for the input 4? So at the 4th position, okay, so it's not 4th position technically, it's the value corresponding to 4, the digit 4. We want the output that the value at this position should be 1. That means it's 100% probability of belonging to that class, and the rest of the values should be 0. That is the ideal output, right? The true class has 100% probability and the rest of the classes have 0% probability because the input doesn't belong to the rest of the classes. So those should be 0. The input belongs to one particular class and that should have a probability of 100%. So the task of the loss function is to map the model output fx to an ideal output like that. Okay, so y is the ideal output, which is the vector where the true class y has 100% probability and the rest of the classes have 0% probability. So that's the ideal output, and the loss function tries to produce this correct ideal output. So
I have a question. If it's you're saying that the 4 should be the 100%, but it's not at the 100%. The 3 is topper than 1. So why the reason is that?
Because the model is not yet perfectly trained. That's why.
Okay.
Yeah. So this model is not perfectly trained, so it is not producing our expected output. So the model should be trained using the loss function to produce our expected output.
Okay.
Yeah. So our input set on which we train, it's represented by the symbols x, y. X is the input and y is the expected output corresponding to x. So this data set, it caters to some particular distribution D. Now actually, mathematically, if we look inside the model, the task of the model is to work on that distribution D. But the problem is we don't know that distribution beforehand. So the model mathematically tries to capture that distribution and map x to y. So if we could know the distribution beforehand, then yeah, then the task would have been a lot simpler. But in the real life problems, we don't know the distribution beforehand. It could be any sort of data, any sort of mapping from any x to any y. So the neural network is designed in a way that that any distribution D could be captured by the model. There is a mathematical theorem also that a single layer neural network can capture any type of function within the universe. It's an universal approximator, things like that. So there they mathematically show that neural network is mathematically a universal approximator. It can approximate any function in the universe, but of course that's hypothetically true. So we don't know the actual distribution D. We have our training data set, and using the data set, we try to capture that distribution. So that's why the issue of overfitting arises. Because we don't know the distribution, we don't know the whole world of data, the whole universe of data. We only get to see a subset of the universe, our training data set, and using that subset of the universe, we try to learn the mapping. So that's why when in the inference setting, deployment setting, we get a slightly different sample outside the training subset, the output is not perfect because the model got to see only a subset of the universe, not the whole universe of data. So the way the loss function works is for all the values in the training data set, let's say we have n values, we in a particular training epoch, we calculate the loss for all those n values, and the loss for that particular training phase is the average of those values. So let's say that we have two training samples corresponding to 4 and 5, digits 4 and 5. So we calculate the losses on both the training samples. So for the first training sample, the ideal output is where the level 4 has 100% probability. For the second training sample, the ideal output is where the level 5 has the highest probability. So we calculate the losses corresponding to all of those cases for all the n training samples, and the average of those values is the loss for that training epoch. And with each training epoch, our goal is to minimize that loss. Okay, so this is a single neural network mapping from the input to the output space. So the input is our the image of handwritten digit. So this input comes from the MNIST dataset of handwritten digits. It's a very popular dataset. So each image in the dataset has 28 into 28 pixel. It's very small image, very grainy black and white images. So 28 into 28, that becomes 784. So here the model takes as input all those 784 values. It is a matrix of values, 28 into 28. So the model just flattens the matrix. So it's a tape of 784 values. That's the input to the model. So we have one hidden layer. No, here we don't have hidden layer. We take the 784 values and map them to the 10 output values. We don't have a hidden layer yet. Yeah. So 784 to 10, that's the mapping. And the weight matrix that is used to map, that's W, and bias is just some values we add after we calculate W into X. Okay. So these are the raw output values here. So we use some function to convert the raw output values to the probability distribution like this. So the output values, they don't depict any probability. We use the softmax function here to convert the output values to a probability distribution like this, where each of the values depict the probability of belonging to one particular class. So we do this transformation because it makes the training better and it's also more intuitive, right? I mean, yeah, like the output should be like the probability of belonging to each of the classes. That's easier to understand, and that also makes the training better. So at the end, we obtain the probability vector P from the input X. So X to Z, then Z is converted to P. So the parameters that are required for this mapping are W and B, and the task of the training function is to learn the values of W and B. These are the parameters of the model. So that's the most basic neural network. So the softmax function, the formula is given here. It's like very simple. It's kind of scaling of all the values. You do the exponential on each of the values, and then you scale it by the summation of exponential across all of the values. So you do a scaling. You scale each value against the sum of all the values. So the training curve should ideally look like this. These are the initial values of the parameters. So when we start training, we don't know the exact values of the parameters. So we initially start from this stage here, and let's say the loss value is like this at this initial stage. Now as we progress the training, we expect that the loss should decrease as it is here. So after a certain number of training efforts for some particular values of parameters, the loss becomes 0. So that's the set of parameters we expect to obtain here. So any values other than these will degrade the model. So when the values are changed both in this direction and this direction, the loss function value is increasing, meaning that the model is getting worse. Only at this optimal point we have the loss value 0, which means this is the ideal set of parameters. Okay. So in an ideal world, in a utopian world, this is how the training looks like. Okay, we start from some values, we obtain some set of values for which the loss is 0, and that's our final values. That is our ideal set of values. But the problem is that in real world, the training is not like this, as smooth as this. So here it looks, it's very easy, right? You start with a certain set of parameters that correspond to a certain value of loss. With the training, you decrease the loss. So as the loss decreases, you are changing your parameter values corresponding to those decrease of loss. So finally, you obtain a set of parameters for which the loss becomes 0. These are your parameter values. Very simple mapping, but ideal world is not like that. What can go wrong here? What can make this process less ideal than what is shown in this diagram?
I mean, we don't want loss to be 0, right?
That's a very good point. We don't want loss to be exact 0. Why?
Because that's actually a sign of overfitting, and that you're
Very
just.
good. So we don't want the loss to be exactly 0, because that could mean overfitting. That means that your model is memorizing your training data. So ideally, you don't want your loss to be exactly 0, technically, because in most of the cases that would lead to overfitting. What else?
Testing accuracies.
Sorry?
I mean, we'll train a model, right? We'll extract training accuracy and testing accuracy.
Yeah.
So the training accuracy should be almost equal. So in that case, loss should be almost equal to the training accuracy. So in that case, the model might be underfitting as well.
Yeah. So yeah, overfitting is an issue which can happen to this ideal setting, which can make it non-ideal, and it happens in real life. What else can go wrong? Okay, so we are seeing like a smooth convex function that starts from a certain point, then very smoothly it reaches to 0, and then again smoothly increases as we go beyond this ideal set of parameters. But what if this curve is not like this? So here you see that because the parameters and the loss function, they follow this curve, you can smoothly train from a certain loss. You decrease the loss and you obtain an ideal set of parameters. But what if the function doesn't look like this?
Then it's kind of hard to know whether, like, where you're at with, like, whether you're making progress or not, or whether you overfit or not. If it's going, like, you're saying, like, it's like up and down for, it gets 0, maybe going down for a little bit, then going back up randomly. It gets
Okay,
kind of messy.
Go to the blackboard a little bit. Okay. Okay, so that's the kind of very good shape, convex shape. This is convex, where we can smoothly proceed from a certain initial state to a kind of expected set of parameter values. The training can proceed smoothly. So what if the function now looks like this? This is the loss. Sorry, this is theta. Let's say that we start from this initial state here, okay? We start from here. This is a point A. And this is actually our expected set of parameter values. Here we see that the loss is minimum. Our goal is to reach this point. Let's say that this is G. So what will happen? Let's say that we are going along this direction, okay? Then we reach this point B. And then we see that as we move from the set of parameters here to this direction, loss is again increasing. So what will our model perceive? It will perceive that B is the solution. Okay, the landscape it is viewing, it can see that, okay, as we go around the neighbors of B, the loss increases along both directions. So B is the minimum that it can obtain. It will say that the output is B, but the output is not B. The output is here, G. So this is one problem that occurs when the curve of the loss function is not a bowl-shaped curve, not a ideal convex-shaped, bowl-shaped curve. So then it can be tricked into assuming a non-ideal solution as an ideal solution. So this kind of solution is called a local minimum. So this point here is minimum within this local landscape, within the neighboring landscape. But this is not the global minimum. This is the global minimum. Which is the ideal value within the entire universal landscape. So when we have function whose curve looks like this, then we end up with local minimum, which is not our ideal solution that we expect to obtain. So that is one issue. And of course, another one you mentioned, that's overfitting. Okay, so when we have a situation like this, what could be the solution to get the local minimum? What can you do to your training function so that it can escape the local minimum?
We have to give it some option to go up a hill again, and go back until a certain point, I guess. Like even if it finds the lowest point, keep going until we have to, I don't like a timed restraint
So
versus
the
just the
problem is
minimum.
that we don't get to see curves like this. This is unknown to us. We don't know what the shape of the function looks like. We only get to see the values along which, we have a certain direction to proceed, and we only get to see during a certain epoch, the neighboring landscape. So what the values and the loss function look like in your prior training epochs, what's looking like in your later training epochs. So you only get to see that landscape of values. So when the function doesn't look like that, the solution you mentioned, that's good. But how high will it go? So you're saying that you will allow the loss function to increase up to a certain point.
Yes, give it a higher, allow it to keep increasing to a certain point.
Okay,
Yeah,
so here as we go along the up direction, we will see that, okay, we are moving higher and higher. So how far? I mean, if the function actually looks like this, you will go as high as to the universe, but your global minimum was here. You won't reach any minimum. If the function looks like this, the ideal case.
I don't know how to say it mathematically, but is it okay for it to find essentially what I wanted to do is find there's the first local minimum, then after you notice the data going up for a set amount, then be on the lookout for another minimum and then compare the minimums.
Okay. But
can we try regularization?
yeah. We will come to that topic later. So yeah, regularization is of course where you manipulate the parameter values theta. Yeah. So that actually is not a perfect solution to this problem, but yeah, that's of course one of the things we will discuss later. So what else? Let's say that we do the training like this, just like this. So we start decreasing the loss function, and after a certain point we will see that, okay, the loss function is again increasing because you obtain the minimum loss at this point. So, but that minimum, it's not the global minimum. So this problem, this is true for all machine learning algorithms. This is not only for neural network. This is true for all machine learning algorithms because machine learning works on data, and it assumes that for the data corresponding to that data, you have an ideal set of parameters for which you obtain minimum loss. So when you move away from that ideal set of parameters, the loss is supposed to increase. Only at the ideal point you have the minimum loss. So implicitly it assumes that all of the functions are convex. Any machine learning algorithm assumes that. So when the shape is non-convex, the way to escape this problem of local minimum is to add randomness to the model. Randomness is the solution. You see, you can add randomness in multiple ways, like let's say that you don't always move towards the direction of minimizing loss. Sometimes you explore the other set of neighboring points also. The points which don't decrease your loss, it increases, but you explore those directions because you want to just explore the entire landscape. Things like that. So randomness is the key. So when we don't have randomness in our algorithm, we just follow the rigorous mathematical process, we are bound to end up in regions like this. So randomness is actually very important in computer science. So computer science is not the ideal world of mathematics where everything works ideally. This is the real world we are talking about. And in real world, things can go wrong in any ways, any number of ways. So randomness is a very good thing to avoid some pitfalls with the rigorous mathematical processes. Anyway, this is very theoretical discussion. So here we also show a different way of viewing the landscape. Let's say that we have two parameters, x1 and x2, and these are the two training classes, the blue class and the red class. And we want to find a straight line along this parameter plot which separates the two classes. So the line we wish to obtain is something like this, right? Which separates the blue from the red. But initially we start with the green line which looks like this. So this initial setting, it's not our ideal value because it's not separating the two classes. So after we learn this function, we wish to obtain a line which can separate the two classes. So this is the initial configuration which corresponds to this set of parameters here. So at the end of training, our goal is to obtain the line that looks like this, okay, which separates the two classes, and let's say that this is the final set of parameters for which we obtain this line of separation, expected line of separation. So the goal of the training is to move from this initial state to this final state. So the way we do typically, this is called the gradient descent algorithm, that we initialize the initial set of parameters randomly. Then with a certain number of training epochs, we expect to reach this final state of parameters for which the function is fully trained. So here, during each training epoch, we update the set of parameters using this function. So the updated set of parameters is obtained by changing the values of the current set of parameters along the direction which minimizes the loss function. So this is called the gradient of the loss function or the objective function. So this is the scaling of the values we need to do in order to move towards the direction of minimizing the loss. So when we say that in the landscape we move from a certain point certain configuration to some other configuration, we show that okay, we are moving along the direction of minimizing loss. What we mean is we are calculating this function. So you find the loss function, derivative of the loss function, this value mathematically which takes you along this direction. So you find this value and you update your parameters using this gradient. So in the gradient descent algorithm, we calculate the gradient by using all of the training samples. So using all of the training samples, we find that how much we need to upgrade the parameter values so that the loss corresponding to those set of parameters decreases. We calculate that much scaling based on all of our input samples. That's the typical gradient descent algorithm. And we update all of the parameters corresponding to the direction which we obtain using all of the training samples. So all the training samples participate in each epoch of training here. So during each epoch, all of the training samples are participating. All the n training samples are participating. And using all of them, we are updating the values. So we can do that differently. If instead of using all of the training samples, we use a certain random training sample in each epoch to calculate the gradient of loss and update the parameter values. So that's another alternative to the typical gradient descent algorithm. This is called stochastic gradient descent. So when we are updating using all of the training samples, the training kind of becomes very smooth, right? Any problem? Any problem? Okay. So the training kind of becomes very smooth. We smoothly move from the initial set of parameters to the final set of parameters. But if we do stochastic gradient descent, then it may not be as smooth. There can be oscillations because you are not taking into consideration all of the training samples in each training epoch. You are randomly choosing one value and you are updating the gradients based on that one single value. So here in this case, the path along which we move from theta naught to theta final, that may be oscillating a little bit, because in each training epoch we are randomly selecting one input sample to do that gradient updating. So why might we want to do that? What's the purpose of doing the stochastic gradient descent? Where it kind of, this path, it looks like very oscillating, very zigzag. It doesn't look very beautiful. Here you have a beautiful gradient, beautiful path that takes you from your initial state to the final state. Here you have lots of zigzags in between. So why is this even a candidate? So the difference is that here in each training epoch, when you do one time all the training samples. But here in this case, in each training epoch, you randomly select one training sample and do the training based on that particular training sample. So because you are taking just one training sample out of so many, out of the n samples, so the curve is not smooth like the previous one. It oscillates a lot, because that training sample you choose, it varies from epoch to epoch, and that makes your path very zigzag and non-uniform. So why is this a candidate? Okay, let's see again what we have another alternative to that process. So this is called mini batch stochastic gradient descent, where you kind of come to a middle ground. You are not taking all of the training samples. Also, you are not randomly taking one single sample. Rather, you take a subset of the samples. This is called a mini batch of samples. So based on the mini batch, in each training epoch, you select one mini batch of samples and you do your parameter update based on that mini batch. So this is the full set. This is just one member out of the whole set, and this is just a subset. Here you are updating based on the subset of the whole set. Okay. So why do we have three versions of gradient descent instead of just this one? Because this one looks the most ideal. Your training should take into consideration all of the training samples. You have it all, you should use it all, and you obtain a smooth curve when you use all of those. But when you just use one, you have a very non-uniform path. So when you use, instead of one, you choose a subset, then the path becomes more uniform, but it's not as smooth as this one. So why are these even candidates for training?
Make the model perform better to learn more from the data so that we can use.
Okay. So yeah, obviously they should have some benefit. These stochastic algorithms, they should have some benefit, right? Obviously, because that's why we are learning them. So we don't have to memorize these algorithms, but when you implement neural network, you have to choose whether you use the batch or stochastic or the full gradient descent. You have to choose like that. So why are those options? How do they make things better?
Based on the data, I mean, like if it's certain data, if you want a certain parameter to be like boosted something, so we can go with that particular like group one stochastic. Sorry.
So okay, good one. So how do we know which one is good? Here we are just randomly selecting one sample. Here you see there's no goodness criteria.
Group one basically.
Actually, we are trying to take random one value, but on that value we are trying to use the gradient descent so that we can get the minimum value out of it. Then we can apply it again to get to the next step.
That's what we're doing here. So ideally it should be like that. When we choose to go along a certain direction, we should take consensus from all of the training samples, right? Let's say that I want to make a decision about your class. So I should want that every one of you should participate. Each of you should participate. If I just, randomly choose one of you and I take the decision based on his opinion, you will all get angry. Like, why? Why didn't we get to participate? So here it is happening like that. All the training samples should participate in all the epochs of training. That's the case. But why are we learning these algorithms where, we are randomly choosing one or a subset of values to participate in training instead of all of the values?
I mean, not all models, not all kind of data sets require the vast computational efficiency. So again, as you said, based on the kind of data set we are handling, we need not to train the entire data set for everything. So I think in that cases, the stochastic gradient descent.
So how do you know which data set is which type? Okay, so yeah, you have given very good responses, all of you. Thank you for that. But the actual reason why we are doing the stochastic algorithms is because we want to introduce some randomness. Randomness is the key. Like we discussed before, that it's not always the case that, going just downhill direction will lead you to your solution. You need some degree of randomness in your algorithm. You need to randomly explore the landscape somehow.
So it is basically mix and match.
Yeah, kind of mix and match. You need to introduce randomness somehow in the machine learning algorithms. Randomness helps you, avoid many sorts of pitfalls like the one we discussed here, local and global minimum. So that's why we do the stochastic processes. Stochastic means probabilistic calculation. Always, whenever you see the term stochastic, it will mean that there is some randomness in the algorithm. So yeah. So that's why we do the stochastic processes. And in fact, when you train the neural networks, you will see that in most of the codes, you will use the stochastic algorithms instead of the original gradient descent. This stochastic is the choice, and most of the times you will do the mini batch stochastic gradient descent. Mini batch is easy because that gives better solution. dogs, and the training data kinds of contains these photos of cats and dogs, the side profiles, okay? But when you are deploying it, the images you obtain, they are, just the front profile, images looking like this. So, what do you think? The model which is trained on images like this will be able to determine on images like this, here, side profile versus the front profile.
No.
You can check that when you run your own models, but you see that overfitting is a very major issue, because not only this is a difference like side profile versus front profile, but when that difference is not as apparent as this also, like the images just slightly vary. Let's say that the lighting in your room just slightly varies. In the training set, let's say that you have very bright images, but when you deploy, you give an image which is not as bright, kind of a little dim. Then also you will see that your model is not able to recognize. I mean, overfitting is that crucial. In real life settings, if a model is not trained well, most often it only works when you just give copies of the training samples to the model. Then only the model is able to do the prediction correctly. But little changes like the brightness, the type of background or screen, when you changes even things like that, the output changes dramatically. Sometimes even color. I mean, you train, let's say that all the images with blue background. Then when you are testing, you give an image with red background, and yeah, you end up with the wrong label. Overfitting is this much of an issue. And the irony is that powerful models are more likely to overfit. Yeah, so why is that? We will see what we mean by powerful model later, but let's say that the more capacity your model has, the more likely it is to overfit. Why is that?
Is it
It's taking on more
because
data? Like it is being trained a lot, something like that. That's why it's over.
Let's use the analogy of students preparing for exams like we did last class. Okay, so what this statement means is that the better the student, sometimes the more likely he is to memorize. Better students memorize more.
Trains on the same data mostly, so it can't handle the other data.
No, that's true for all models, right? So why it is the case that the powerful models are even more likely to overfit?
is it because since
Because
there's
it's learned
more,
everything what needs to be there, and it's fitting everything according to whatever we desired. Like we created the model in such a way that it sees all the values, all the errors, minimize it. It didn't learn from itself. It's learned from us. It didn't learn itself. That's why the model is like overfitting.
Yeah, that's the overfitting issue. But why it is that when you build a powerful model, let's say when the student is better, when the student is a better performer, he tends to memorize more.
Yeah.
Training on
It's-
more labeled data.
is because there's more layers, then is it more of a chance for it to just pick up the exact context instead of just a peculiar feature? Since there's more layers, more of a chance for it to, because each layer of neurons can just choose a feature.
Your answer is very close.
Okay.
This is the correct answer, but let's look at it from the perspective of our analogy. So what will happen for a good student? He will strive to do the best in his exam. So what if there are only, let's say, a few questions to prepare for? Let's say that there are only 4 or 5 sample questions to prepare for. Because the student wants to learn more, he wants to sit in his desk and learn for 20 hours. So that's not 20 hours of content, that's only 4 to 5 questions. So let's say that takes only 1 hour. So what will he do for the rest of the 19 hours?
Study
He
the
will
book.
read and read and read until he just gobbles all the contents, and it reaches up to a point when he loses all sorts of perspective. I mean, he actually continuously reads all the questions, and those questions become his world.
So
So he drastically underperforms in the exam. Ironically, if the student is, let's say that not as serious, he will just, spend 30 minutes looking at those questions, get an idea, and then in the exam, he will just try to create something of his own. So that will give him some marks, some partial marks. But the better student who just memorized all the contents, he will, write all those things in the exam and get even 4 marks. So the problem here is that when the model has more capacity, it has lots of potential. So we need to provide it with data which fulfills its potential. That's the problem. So when we have very good and large data set, then the large models, they perform very good because they have contents to learn from and they have the capacity to learn, so they perform better. But when we have the capacity but don't provide the contents, that's when it fails. So we also saw that the overfitting issue can be avoided by keeping a set of the training data aside for validation. So when you have a small number of data to begin with, then you choose some data for validation. Then you remain with very few number of training samples. And when your model is powerful, that is too few for the model to learn from. So that's why the model kind of learns even worse compared to a weaker model. So as we proceed with the training, we expect that the training loss decreases with each training step, and the validation curve looks like kind of this. It follows the training curve up to a certain number of training steps. After that, the more we train, the worse we become, because beyond that point, we have the issue of overfitting. We are seeing that, okay, the training loss is decreasing, but actually beyond that point, the model starts memorizing the data. So the training loss decreases, but the validation loss increases because memorizing doesn't help the model. So when you train neural network models, there are tools to generate curves, training curves, and this is the shape of the curve you want to obtain. So the curve should not be something flat or any other weird shapes. If your curve looks like this, then you can be sure that, okay, your training is going well. Your training is good. Okay. So in the next class, we will discuss some of the techniques to reduce overfitting. We'll be done with discussing the basics of neural. So there are two very good approaches to reduce overfitting. One is called dropout and the other is called batch normalization. So these are the kind of tools that everyone uses these days, and it's available in all of the frameworks for use, and they help the training a lot. Any
Do we
question?
need to make any videos of
Thank you.
I don't think so.